on lab like Christina. We'll get a closer look behind the scenes at the facility she's in a moment. But first, let's go to you, Jessica. Jessica Clark, fault protection engineer. Let's start with that. Let's unpack that a little bit. What is fault protection?
Yeah, thank you, Stephanie. So fault protection is kind of a unique field at JPL. And the metaphor that I sometimes hear people use is that we're kind of like the doctors for the rover. So because there's nobody to take care of the rover on Mars or en route to Mars if it encounters an issue, we actually have to equip Perseverance with the ability to diagnose problems on itself. So we build in all of this software to help Perseverance detect if something has gone wrong. And then there actually are several spare components that she can use and swap to if she encounters an issue. So in addition to that, we kind of operate like the doctors in operations once she's on her way to Mars, because if there is a problem, Perseverance notifies the team on the ground, and then we work to try to diagnose what's going on and try to get her back to full operations.
Now, you're at home right now. You'll be on console at JPL tomorrow. What will you be doing?
Hopefully not getting too nervous, but really just getting excited. And our team is going to be looking at the data coming from Perseverance and assessing whether everything looks nominal, both before the launch and then after we launch. Once we launch, we'll actually have about 45 minutes or so before we go into what's called an eclipse. So we'll go behind the Earth and the sun will be blocked out. And during that time, we will separate from the rocket. And so that period of time we'll actually lose data, lose visibility. And then when we come out of that eclipse, we will begin receiving data from Perseverance's own radio. So that'll be a huge event where we're looking forward to seeing data for the first time being transmitted by Perseverance on its own radio.
I can't wait to see what the shot looks like out of mission control, although you'll all be social distancing, so maybe not quite as many high fives, right?
Correct. Yeah, we actually have had to do a lot to kind of work in this new realm with COVID. So we have very strict cleaning guidelines when we come into our console. We're all going to be wearing masks, so you won't really be able to see us smiling ear to ear. And then, our typical jumping up and down in high fives, you probably won't see us doing that. And we are going to try to eat peanuts, which is a good luck tradition, but we will be doing it in a very discreet and safer way, but still want to try to carry that tradition through.
Fantastic. All right. So I've got a million questions, but that pales in comparison to the number of questions who are coming in from people online. And I want to make sure we get as many as possible. So over on Twitter, Fragile Fern has a software question for you. So speaking as a software developer, she's curious, what programming language do you use to control various functions on the rover?
That is a really good question. So I actually don't write the software, but we do what we call specify it for our software engineers to go and write the code, and it's all in C. So you might be familiar with that. And it's there's no special JPL language that we use.
Excellent. Now I'm just scanning through here. Let's see. Cameras. May I ask you a question about the cameras?
Sure.
All right. So here we go. Amal on Twitter wants to know, how will Perseverance clean its cameras? What if dust particles cover it?
That's a really good question. So I'm not quite as familiar with the cameras, but I do know when we land, we were worried about dust accumulation from landing itself. So the cameras are equipped with dust covers that then once all that dust has settled and we've been on the surface safely, we pop them off. if after that fact there is some dust accumulation, I don't think there's that much we can do other than kind of rely on the ambient winds to clean them off. But I know on MSL, which has been on the surface of Mars for years now, we haven't had any major issues with dust accumulation. So I think we're kind of hoping for the same thing.
All right. And, a lot of folks want to know, how do you even get a job like this? What was the path that you took to get to JPL?
Yeah, it's kind of a winding and seemingly random path. You can't major in fault protection engineering in college. So I realized I wanted to be an engineer around when I was a senior in high school. And I applied to Georgia Tech. I switched majors 2 times. I went from undecided to biomedical. I thought I wanted to be a real doctor, then realized that wasn't for me. So I went into aerospace engineering and just happened to kind of fall in love with it. And through that, I got internships at JPL. And that was a great way to kind of get acquainted with JPL and how NASA works. So through that, I got hired at JPL. And then fault protection, again, was something I had never had prior experience in, but I actually completely love doing fault protection engineering, and I don't know if I'll ever kind of switch out of it.
Fantastic. Okay, so I want to make sure that we get to all of our panelists here. So Jessica, hang on. We're going to switch things over to the Jet Propulsion Laboratory, where Christina Hernandez is in a very, very special place, one of our indoor Mars yards. Christina, tell us more about the lab you're in and what's going on there.
Yeah, so thanks for having me. So right now I'm in the flight software test bed. So it's basically an indoor Mars yard. And we do have COVID protocol, but I took my mask off, my Mars 2020 issued mask, since nobody else is around right now. But basically behind me, what you have is the start of the twin that will eventually become Mars Perseverance's twin. And what we do in here is we test the higher level behaviors of this robotic geologist and astrobiologist. So behind me, we've got the robotic arm in the stowed configuration. And at the very top, we have the turret. And on the turret, we'll have SHERLOC. We have SHERLOC on the other side. And on Tuesday, the Pixel EM sensor assembly, one of our other science instruments, will be getting installed for some robotic arm testing. And so we test all kinds of things. We take images with the instruments, we look at rocks, we drill rocks, and we try and test the end-to-end behavior that we're going to see once we get to Mars.
Fantastic. Now, I know that you are an instrument engineer currently working on Pixel. What does an instrument engineer do?
It's a fun job. Sometimes it's a little chaotic, but I think that's why we all became engineers, to solve tough problems. So instrument engineers, their job is to understand the rover and how it interacts with the instruments, but at the same time, understand all the nuts and bolts and behaviors and quirks, as we call them, of the 7 different science instruments. So we have a team of instrument engineers who have been a part from the early design and accommodation of the instruments on the rover, through assembly, test, and launch operations, where we were testing with the flight vehicle and with engineers like Jessica on console. And then now we're getting ready to prepare for our operations and understanding what are the tools that scientists like Joby, that you'll hear from later, are going to need to do cool science on Mars.
Okay, so question from our YouTube chat. Laxmi Pandit wants to know, how was the rover built? So please.
Oh. It's just such an exciting question, because this is not the effort of a few engineers. It's the effort of not just the United States also, but our global collaborators in France, Norway, and Spain, and many other places. So basically, we had different groups of teams build the boxes, the instruments, the different subsystems. Most of it was built here at JPL. And at JPL is where we integrated and assembled it all together. And so it started from a paper design about 10 years ago, and now it's manifested to a 1-ton beast of a thing that's on a launch pad today.
Fantastic. Oh my goodness, we're getting so many questions here from all over the world. Ah, fantastic. All right, I'm seeing several here where multiple of you are going to be able to weigh in. And so I'm going to wait and hold those for a few minutes in the show here and switch things over to Joby. Thank you, Christina. We'll be back with you in just a moment. Now, Joby Hollis, astrobiologist, postdoctoral scholar working on the SHERLOC instrument. Let's talk about what all of that means. What is astrobiology?
So astrobiology is basically the study, mostly theoretical at the moment, of what life could be beyond Earth. So the question of like, if life existed on a world like Mars, what did it look like? Was it made from the same molecules of like DNA that we are, or was it made from something completely different? So a lot of this is kind of like investigating the kinds of molecules that might be available on other worlds and trying to work out, well, how would they fit together? What would you expect to see billions of years later? How would life survive in such an extremely different environment like that of Mars, or, for example, another world like Europa? Now, obviously, we have only discovered life on one planet so far, Earth. So a lot of this is quite like investigative. Like we're still not sure what we're looking for, but we're pretty certain that when we find it, we'll know.
So Eduardo over on Facebook has a question for you. You mentioned looking for molecules and possibly new molecules there on Mars. He wants to know, is it possible to find a new chemical element on Mars or another compound that might not exist on Earth?
So in terms of elements, those are pretty well established. We've discovered pretty much all of the sort of naturally occurring elements that form through stellar fusion or supernovae, that sort of thing. So that's kind of everything up to iron and beyond. The super heavy elements that are still being discovered these days are being made in particle accelerators. So they're not really something we would expect to find like naturally occurring on the surface of a planet like Mars. When it comes to chemicals and molecules, there's a huge number, like almost infinite number of possible combinations, atoms that can make molecules. Now, some of them are unstable, and we would not expect to find them. The ones that make up us, so we comprise of DNA that has 4 distinct nucleobases in it. So those are A, C, G, and T that you might remember from biology classes at school. Now, it's quite possible that alien life might have something similar to DNA that just uses a slightly different set of molecules. So, you add a methyl group there, you put a nitrogen somewhere else, and suddenly it's a slightly different molecule, which means it may not be compatible with us, but it could still be a valid way of building like an information storage system like DNA, something that could be passed on and from one organism to the next. So we don't really know what to expect. We're sort of working from what we know on Earth. So we're looking for stuff like DNA first. We have certain ideas about life needs to be somewhat complicated to be able to do clever things like metabolize and reproduce. That involves a lot of quite clever chemical machinery. So that requires a certain minimum amount of complexity. So we're looking at lots of different molecules put together in a way that we have not yet observed in any of the studies we've done of organic molecules from things like meteorites. Samples of Mars that have crashed on Earth from hundreds of millions of years ago. We found organic molecules, but they're all extremely simple, stuff that could have just formed through natural geochemistry, so like the chemistry of rocks. So they could be the building blocks of life, but they are not proof of life.
Now, on that note, Keisha over on Facebook wants to know, how do you define life?
Okay, that is a very big question. I do not feel like I am qualified to answer that. I'm not sure if anyone really is qualified to answer that. But certainly in terms of the life we see on Earth, there's some disagreement about whether stuff like a virus is a living thing, because it usually co-opts the chemical machinery of another organism to be able to reproduce. But generally, life as we know it consumes energy, it creates complex structures that wouldn't occur spontaneously, and basically reproduces, so kind of makes copies of itself. So right now, the molecules we found on Mars through previous investigations, so for example, the Viking landers, the Curiosity rover, they found very, very simple molecules, but they're all stuff that can occur through just natural chemistry. They are not proof of life because they're just not complicated enough that we cannot ignore any other possible explanation.
Well, okay, now that you've tackled one of the biggest questions out there, thank you. It's all just going to be so much easier from here on out. And not one of us can do this mission by themselves. So at this point, let's bring everybody back and start to get some perspectives from everybody, because the work that the three of you do as part of this mission team with thousands of people on it is all interconnected. We've got scientists asking the big questions, and we've got engineers figuring out how do we make and use the tools that we have to answer those questions. So I'd like to start off this group discussion, or group portion of the discussion, with looking at how is this rover, how are the instruments on this rover going to help us specifically try to fulfill that mission goal of finding evidence of life, ancient life on Mars. Do we want to start with okay, you can Rochambeau. Do you want to start with the hardware or with the science?
I was going to start with the hardware.
It seems simplest. Let's start there.
Yeah, then we'll have Joby finish it up and polish it off. So we have 7 instruments on the rover, and when they were selected with the intent that they should all complement each other to meet one of our that science objective of looking for signs of ancient life. And so we have 3 spectrometers on the rover: SuperCam, SHERLOC, and Pixel. And they're going to be using chemistry and astrobiology processes to try and understand, what chemicals and organics are present on the samples that we'll drill up with the rover. At the same time, though, we need context. And that's one thing that I appreciated being an engineer is if you have a piece of data, you need the context of where that data came from. And so all of our other instruments like RIMFAX, our ground penetrating radar, META, our weather station that's going to understand humidity and pressure and that sorts of thing, MASCAM-Z, that's kind of like the eyes of the rover. All of these instruments are really contributing to understand the context of the samples that we take. And I don't want to forget MOXIE, because I didn't mention MOXIE, but MOXIE is going to help us with a separate big goal. But I'll let Joby finish it off with the science aspect.
So these instruments, they've been selected to try to catch as wide a range of data as possible. So, for example, Pixel and SHERLOC on the rover's robotic arm, they were both designed to scan the surface of a rock. Yep, Christina's pointing to them, which is awesome. They scan the surface of a rock. They're looking for slightly different things. So SHERLOC is particularly sensitive to organics, and the aromatic organics, which are kind of made by that can be made by living things. So, for example, the nucleobases of DNA are aromatic organic molecules. So SHERLOC is particularly sensitive to those. It can detect them down to 1 part per million. So if there's even a trace left behind in the rock, then we should be able to find it. Pixel will tell us about the elemental composition.
Let's pause there for a second. When you say aromatic, when I, as a non-specialist, when I hear that, I think something that smells very good. Is SHERLOC literally going to sniff out these chemicals on Mars?
Not exactly, no. So we're using a laser to scan the sample, and we look at the light that comes back from the rock. And some of that light has been scattered or re-emitted by the molecules in it. The reason why those molecules we're interested in are called aromatics is because when they were first discovered, 100, 200 years ago, they were generally associated with things particularly like rich smells, right? So a lot of these molecules have very, very distinctive smells. Unfortunately, some of them, if you open a bottle in the lab, everyone can immediately tell because some of them stink. But they happen to be very energy-rich molecules. They're very good at self-organizing. They can be used to create interesting kind of chemical reactions. So they are often the building blocks of molecules like DNA. Also proteins, so 3 out of the 22 amino acids that make up all proteins in living things are aromatic. So if we find a collection of these different aromatics all localized in the same place, and they're all sufficiently chemically complex that they cannot be explained by like a simple geochemical process, then we have to start considering the possibility that they may be what's left over from a biological process. And if we did find something like that, the first thing we would be doing would be taking a sample, storing it in a tube, and bringing it back to Earth in, I believe, 11 years' time, because we want to do more studies. So Perseverance is like, has these amazing instruments that are going to give us a fantastic amount of contextual information, but it pales in comparison to what we can do on Earth with all of the labs we have at our disposal here. So the main priority is, if we find something really cool or really interesting or just really strange, we're going to try and bring it back.
Excellent. So you touched on the sampling system of the rover, the fact that this rover will be the first one to cache samples of the red planet for eventual return to Earth. Whether that's in the 2030s, NASA and ESA are still working out the plans for that. And Abazi over on YouTube wants to know, let's see, is there any possibility for Perseverance or any other NASA missions to return to Earth? This is a really one-way trip. Yeah. for this rover, right,
yeah.
Jessica?
Correct. Unfortunately, it takes a lot of energy just to get something the size of Perseverance to the surface of Mars. So to return it or even the tubes back to Earth requires a lot of propellant. So for this particular mission, it's a one-way trip to Mars. But as we were kind of insinuating earlier, there's a longer-term vision of a Mars sample return that would go and retrieve those sample tubes and bring them back to Earth.
So yes, it may take us a long time to get those physical samples back, but we're going to get data a lot more quickly than that. Faye over on Facebook wants to know how long between launch, arrival on the surface, to transmission of photos? When can we reasonably expect those first images, Jessica?
That's a good question. I actually am not sure. I could imagine it happening relatively quickly, though. We do have communications, during landing and then subsequently following that landing. So we have good coverage. We have a kind of slower data rate at uplinking data once we're on the surface of Mars. So it might take us a little while, but I would say it shouldn't be too long that we're waiting to get those images. At least thumbnails, so smaller sized images,
right,
after we land.
Back with the Curiosity landing back in 2012, I think all of us were just cautiously optimistic that we were going to get photos, and the thumbnails came almost immediately. So I hope Curiosity has not set too high of a unreasonable bar for what we're going to see on landing day. But I'm skipping a few steps. We've got to get this rover launched and to Mars first. And then over to Jezero Crater. So here's a question from Charlie on Twitter for you, Joby. How did you pick the landing site?
I wasn't involved in the decision at all. It happened just before
before I arrived at JPL.
No, unfortunately not, but it was a collective decision made by hundreds of scientists who are obviously Mars scientists invested in the mission and the general exploration of Mars. So they had a number of sites to choose from. Jezero Crater was selected because we can see from orbital imagery that it appears to have been a lake. Roughly 3.5 billion years ago, it looks like it was a lake roughly 250 meters deep. So there was liquid water on the surface of Mars at one point. And what's more, we can see a river channel that traveled into the lake, and you can see a river delta that'd be left behind. So that's kind of like a big fan of deposits of minerals like clays and carbonates that were carried by that water and dropped as the river entered the lake. So obviously we can't see any liquid water now, but we can see these kind of remnants of what used to be a flowing water on Mars. And those deposits, those clays, those carbonates, based on what we've seen on Earth, they tend to be very, very rich in organic material. So anything that was living in that water could be preserved over billions of years in those deposits. So by landing in Jezero Crater, we're getting immediate access to effectively a geological and potentially an astrobiological record of what was going on in that water system. And that's going to be incredibly invaluable for understanding the history of Mars, and especially things like, was Mars habitable 3 billion years ago? Did something ever evolve and live in that water?
3 billion years can leave a lot of sediments behind. And I have a very practical question for you, Christina, from Edgar on YouTube, who wants to know, how deep can this rover drill?
That's actually a good question. I don't know if you know it, Jessica. I do know, though, that we have the ability to image the subsurface of Mars. I kind of alluded to this earlier with RIMFAX. And so you could imagine RIMFAX giving us some context of what's underneath the subsurface, and then the coring team coming in and taking some samples. But I don't think it's quite deep. We've sent other landers like InSight, for example, that were able to penetrate much deeper. We're really trying to just get right below that subsurface.
If
Perseverance's drill is 5 centimeters, I believe.
There we go. So it's the same, on the same order as the Curiosity rover, which is currently up there on Mars. I think it's getting a final taste of the clay unit right now. So we love all our robots, right? It's not just about Perseverance and our whole Mars exploration program. My goodness, we've got so many people around the world working on this who are so excited. And I just want to make sure that everybody has really just had a chance to get to know all of you today, to see you. And before we wrap up this show, I want to ask, how are you feeling? How are you feeling as we head into launch?
I don't
think I'm going to get much sleep tonight.
So not much sleep from Joby. Jessica, how are you doing?
I'm doing okay, actually. I have a strange sense of calm, even though tomorrow we're going to be on console. And I think the biggest thing is I'm just trying to shift my sleep hours so that when I wake up at midnight and go into work, I won't be completely zonked. But I'm excited. I'm ready.
And how about you, Christina?
I'm super excited because with the launch, it means that it's time to do more testing to get ready for the surface of Mars. So there's a lot of work to do.
All about job security for you then, right?
Duh.
Well, fantastic. I want to thank you all for your time, and for everybody watching online, thank you for the fantastic questions. We hope that you will be watching live with us as Perseverance lifts off for the Red Planet. Our launch coverage will start at dark 30 here in the Pacific time zone. We'll be going live at 4 a.m. Pacific, 7 a.m. Eastern, 1100 UTC, with liftoff expected about 50 minutes later. And we will be streaming live on NASA television, the NASA website, YouTube, Dailymotion, LinkedIn, Facebook, Twitter, and Twitch. Don't forget that you can follow the rover at NASA Persevere on Twitter and Facebook. All of us here at JPL, at NASA JPL, wherever you get your social, and all of NASA's missions at NASA. Don't forget to use the hashtag Countdown to Mars to join the conversation. Be safe, be well, and we'll see you online.